Welcome back to part 2 of this lecture in natural language processing. In this lecture, we will be talking about classical text representations. So just to recap from last time, a text representation, which is the main focus of this lecture, is a way of representing words as vectors of numbers. So we saw this example last time about king, queen, man, and woman being represented as vectors. So this is the ideal picture that we would like to arrive at. So there are many different ways of representing words. So one method that we can utilize here is the bag of words representation. So this is one of the simplest kinds of representation methods. So in this example, we will be dealing with two sentences. So the first one we saw last time as well. I really liked Ali Smith's new book. And the second one is Ali really loves books. So if we want to produce or compute a bag of words representation, we start by enumerating all the unique words in the corpus. So when dealing with natural language processing, a corpus is simply a sequence of documents, where again, recall that a document is simply just any text. This could be a sentence, it could be a whole article, it could be whatever is your unit of text. So in this case, we would have two sentences corresponding to two documents, and our corpus would be this collection of two documents. Okay, so we enumerate all the unique words in the corpus. This collection of unique words is also called the vocabulary because it corresponds to the vocabulary that our model will know about. We have I really liked Ali Smith's new book, and then the extra words that was not included in the first document, which are included in the second document, are these loves and books, because Ali and really already occurred in the first one. So we now have our vocabulary. So now for every word that we're interested in, so all the words that are appearing in our corpus, we associate the one hot vector. So one hot simply means that to every word we associate the vector which is all zeros except the position the word corresponds to in the vocabulary. So the word I, for instance, corresponds to the first spot in the vocabulary, so we put a 1 there. And Ali corresponds to the fourth place in the vocabulary, so we put a 1 there. So it's called one hot because there's one position in this vector which is hot, or which is 1. That's where the name comes from. So now we know how to embed every word using this bag of words representation. I should also mention that I will use the words represent and embed as synonyms because that's how they are usually used in NLP. So representation and embedding, they are exactly the same thing. It's just a way of converting text into numbers. So this vector we see here, we could call that a representation of I. We could also call it an embedding of I, whatever you prefer, it's all the same. So going from words to documents, we can now embed a document. For instance, I really liked Ali Smith's new book by simply adding up the word vectors. So this means that from this vector, we can see that this document contains the word I really liked Ali Smith's new book, and we can also see that it contains every one of those words exactly once. In contrast, the second document contains the word really twice, which is why we have a 2 here in the second place in the vector. And this is it. This is the representation, bag of words representation of these documents. So if we want to visualize how the bag of words representation looks like, we see that since every word is associated with its own unique dimension, all these vectors, like the vectors associated to man, woman, king, and queen, they are all independent. They are lying in different dimensions of this space. So we don't get any, or we don't see any correlations between king and queen, like the kind of royalty correlation, and we don't see the gender correlation between man and woman, or like woman queen both being women, and man king. So we see none of that in this representation. Furthermore, we also are giving equal weight to all words. Since we just associated them with a single one in their dimension, man is of equal importance to king, and woman is equally as important as queen, even though queen and king, one could argue, would be rarer in a corpus. So it should have more meaning or more emphasis on that particular word. So just to mention a few of the downsides of this representation, or the features that this representation is lacking. So I've mentioned this already, that it applies an equal weight to all words. So very frequent words such as the in English is suddenly as important as words like COVID-19, which in the grand scheme of things are more rare. Secondly, it does not capture correlations between words. So that's what I mentioned between, say, queen and woman. It does not capture the correlation between those. Thirdly, representation is static. So for every word, we associated a unique vector, which was completely independent on the surrounding words or the context. So in this case, the word apple, the fruit, would be, or would have exactly the same vector as Apple, the company, which should not be the case. And lastly, this representation cannot handle new words that were not present in the training data. Since we only embedded or assigned representations to all words that appeared in our training data, which were just these two sentences in our toy example, if we come across a new word, we would have no idea what to do with it. There is a hack to avoid that, which is to come up with a new dummy word, which is just an out of vocabulary word. And then every time you come across a new word, you just associate that word to it. So it is a hack, and it does work, but it doesn't work satisfactorily. So despite all of these downsides, bag of words representation can still be useful for text classification in some cases. Note that one definite upside this thing has is that it's very easy to compute, which means that computers can compute these things very quickly. So if speed is of an essential concern, this might still be useful. So moving on to the second classical representation in this part, TF-IDF representation it's very similar to bag of words. Like you can think of it as an extension of bag of words. And the main difference between the two is that TF-IDF solves one of the downsides of bag of words, which is we want to assign a larger weight to words that appear less often. So for instance, the word the, which appears really often in English, should not be assigned a large weight. Like we shouldn't care that much about that particular word. Okay, so this TF-IDF representation, it consists of two parts, the TF part and the IDF part. So the TF part stands for term frequency, and this is really just a synonym for what we have just seen. So this is exactly the same thing as the bag of words definition. So for instance, if we look at this document that we saw just before, Ali really, really loves books, we map that to this vector here corresponding to the vocabulary that we saw. This second entry was the word really. This is also the term frequency vector of that document. So it's the same thing as the bag of words. So instead of just thinking of it as a bag of words, we just think of it as these counting the frequencies of the individual terms or words appearing in the document. But it's the same idea, same principle. Right, before we get to the IDF part, we have to talk about what is document frequency. So we could call that DF. So if we have a word W and we want to compute the document frequency of that word, then we simply count the number of documents in our corpus in which this word appears. So if we look at the word really, so if you remember, this word really appeared in both of our documents, and our corpus only consists of 2 documents in this example. This means that the document frequency of the word really in our corpus is 2. Okay, so far so good. Also, before I get to IDF, also note that this is exactly what we care about. Like the word the would have a very high document frequency because it would appear in many documents, but a word like COVID-19, for instance, would appear in fewer documents, so it would have a smaller document frequency. Okay, so we want there to be an inverse relation between the document frequency and the weight that we associate to a word. The smaller or the lower the document frequency is, the higher weight or the more important it should get. So this is why we're not interested in the document frequency, we're interested in the inverse document frequency. So ignore the logarithm for now. So if we look at this fraction here, n over the document frequency, n is simply the number of documents in our corpus. So in our case, just n is 2. So this would mean that if a word appears in both of our documents, this fraction here would just be 1. But if a word appears in only one of the documents, this document frequency would be 1, so that this here would be 2. Okay, so the logarithm is simply there to ensure that it doesn't grow too fast. Like we want to assign a higher weight to rare words, but not necessarily linearly. So this is just like somewhat an arbitrary decision. So note here that the smallest value this here can get is when the document frequency is equal to n. So this here would just be 1. And when we take the logarithm of 1 is 0. So the minimum value this preliminary definition of the inverse document frequency can have is 0. So it goes from 0 and then just upwards. Okay. So we have this preliminary definition, so this is the same as we just saw. And we see that this definition does satisfy that the more often a word occurs, the smaller the preliminary inverse document frequency becomes. Okay. So there is a problem with this definition. So I'll just give you a couple of seconds to think about what could be the problem with this definition. Okay, so a problem with definition, like basically every single time you see a fraction, one of the things that you should think about is what happens if the denominator is 0. So in our case, if we give this preliminary IDF a word that it has not seen before, so it does not occur in any of the documents, we would be dividing by 0. So that's no good. So we have to fix that. So one common way of fixing that is to simply add 1 to the denominator and the numerator. So by adding 1 to both, we ensure again this minimum value of 0 that we had before, and this intuitively corresponds to us adding a new document to our corpus in which every word appears exactly once. So document, essentially just adding the vocabulary as a document to the corpus. Okay, so we can solve that issue. So we have a revised IDF now, which is just adding 1. Okay, it is quite common as well to add 1 to the log, like outside the log, which has the effect of changing the minimum value from 0, as we saw, to 1. And the effect of this is that we never completely ignore a word. So this is the final IDF that we will be working with. And when computing the TF-IDF, we simply multiply the term frequency of the word within a document, document D, multiplied by the inverse document frequency of that word. So here we can think of, because we added the 1, if a document, or sorry, if a word appears in all of the documents, which means that this inner fraction here would be 1, this IDF value would also be 1, like this first term would be 0, as we saw before, and then we add a 1. So by multiplying the IDF, it means that if your word appears in all of the documents, then we're simply just multiplying by 1. We're not changing the term frequency at all. But if the word appears in fewer documents, we are assigning a larger weight to that, to the term frequency. So you can think of this intuitively as we count the number of words in the document, and then we scale up the rare words. So again, we have the same example sentences as before. So just to sum up, to produce this TF-IDF representation, we enumerate all the unique words in the corpus. This is the vocabulary again. We compute the term frequency vectors, so the bag of words vectors from before. We then scale by the inverse document frequency. So we compute these inverse document frequencies for each word, and we multiply their term frequencies by that. And it is also common to normalize the resulting vectors, so divide the vector by its norm. So you can choose to do that or not. Right, so here it does have the same 3 downsides as we saw with the bag of words, but it does fix the first problem, that it does scale the words according to their rarity. So COVID-19 has a larger weight than the word the. And this usually performs better than bag of words because it ignores the common ones and also puts more weight on the rare ones. If we want to visualize the TF-IDF representation, it's the same thing as bag of words in that it's still, all the words are still independent, but the rarer words such as king and queen are now assigned a larger weight, which we can visualize here by assigning a longer vector. So to conclude, bag of words and TF-IDF are 2 classical ways we can represent text as vectors. So TF-IDF vectors are bag of word vectors in which the rarer words have a larger weight. Both methods, however, do not consider the order of the words in the documents. And here, despite their simplicity and shortcomings, these TF-IDF vectors, they do lead to good classification performance in many cases, especially if your classification task is quite simple. And lastly, I have some references here. There are 2 chapters or sub-chapters in Jurowski and Martin covering bag of words and general introduction to word embeddings. The introduction to TF-IDF vectors and their applications in the same book. And then I'm also linking 2 sections of the scikit-learn documentation, which we will be using, which is covering their bag of words implementation and TF-IDF implementation. That is it for this part.